Uh, Now I'm doing a second example of characterizing the output of a linear system, a stable linear system in steady state as time goes to infinity, when the input is a random process. The input to that system is a random process. Here's this example. The input is unity white noise, meaning its power spectral density is just 1. And the transfer function is this generic first order filter, 1 over 1 plus TS. Find the output power spectral density and the mean squared value. Well, here's the formula for finding the output power spectral density. And this guy is easy. It's just 1. And what's the magnitude of this thing? Squared. The squared magnitude of this thing. Well, the magnitude of this guy, first we plug in j omega for s. That makes that denominator a complex term. The magnitude of this is the magnitude of the numerator divided by the magnitude of the denominator. Magnitude of the numerator is just 1. The magnitude of the denominator being a complex number, it's Pythagorean theorem. It's the real part squared plus the imaginary part squared. And then take the square root of that for the magnitude, but we're going to square it so you don't have to take the square root anyway. Anyway, you do all that, you get this. Plugged in j omega for s, took that magnitude and times the 1, and here's what I get. Here's the power spectral density of the output. The input was unity white noise. It has this power spectral density. It's a constant 1 over all frequencies. The output looks like this, a kind of a bell-shaped type curve looking thing. And the bandwidth is, I think, 2 over T. That's where you hit the half power. Anyway, we can start thinking of the system as a filter. It kind of filtered out certain frequencies. And in this case, it's like a low-pass filter. It filters out, or it only passes lower frequencies. It filters out high frequencies. I guess we can talk about that later. That's more of a linear system thing. But now we need the mean square value. Well, there's a few different ways to do that. Here was one. The mean square is this expectation, and it said it was this. It's basically this area under the power spectral density. And we had what the power spectral density was. It was this, so we need to take that integral, clean it up a little bit, you get this. You still got to look it up in a table. So you do all that, and it simplifies to 1 over 2t. So that was one method. Use this formula and evaluate that integral. The easier way in this case is to use the Fourier transform table. From the power spectral density, find the autocorrelation function, and then evaluate it at tau equals 0 to find the mean square. In this case, that was easy because something that looks like this is in the Fourier transform table. Just to make it match the table, I needed to divide by 2t. Then what's left is something that's in the table. And it's this. And if I plug in 0 for tau, I just get 1 over 2t. So that's 2 ways to do it. And then it turns out there's a third way. Mean square also equals this complex integral. And you need to know functions of a complex variable to actually do this. But someone's done some useful formulas ahead of time and found that if you can factor that integrand this way, Then there are formulas for what that integral is, which means formulas for the mean square value. And what you need, C is a polynomial in S, D is a polynomial in S. The D is higher order. The roots of those polynomials, you have to factor this so that the roots are all in the left half of the complex plane. If you do that, you have these formulas. So let's do that for the example we just did. This is now the third way to find the mean square value. Here is what the output power spectral density is, right? Here's one way to write it. G of S times G of minus S times the power spectral density of the input. Well, this is the nice way to do it because that automatically splits up the G part into a part with all left half plane zeros and poles, and another part with right half plane zeros and and in this case, this input ESD was just 1. So that our CS over DS is just this guy here. Its pole is at -1 over T. That's in the left half plane. There is no 0, so we don't have to worry about that. So that breaks up like this. It's a constant over a D1 S plus another constant. Remember these? Yeah, these are the formulas. In this case, we're just using this first order formula. Yeah, these coefficient, the subscript of the coefficient is the power of the S. So this C sub 0 is 1 over T. D sub 1 is 1. D sub 0 is 1 over T. Plug those into your formula. Simplify, you get 1 over 2T. Matches what we did at the other two ways. I'll save yet another example for another video. So we have 3 ways to find the mean square value. And it's you don't always know ahead of time which one's going to work or which one's going to be easiest. So that's part of the problem.